As you may have seen, I recently visited the Computer Museum of America, and while I was there, I picked up a few souvenir items, including this one here, which is a counters binary. It cost me $35 or around £25. Through the packaging, we can see there's some kind of chip inside, but without further ado, let's open it up and take a closer look. Okay, so here's the main item. It's got some nice Computer Museum of America branding, as well as a bold 6502 on the left-hand side here. And if we look closely at the chip in the center, we can see that it is a WDC, or Western Design Center, W65CO2S, which is a modern version of the original 6502 processor by MOS Technologies and later Commodore. We also get an instruction leaflet and this piece of black plastic, which actually turns out to be the stand. Okay, so before we go ahead and break anything, let's go and read the instruction leaflet to see what we have got here. And when we look inside, we see we have a desk ornament. It says we can count on this to be a great addition to any desk. Watch the beauty of math unfold as this desk ornament displays the patterns created by the base 2 or binary counting system. It shows us what to look out for on the device, including the binary display here on the front, a speed control which changes how fast the display changes. On the back we have a power switch and a reset button as well. The instructions also contain information on how to read binary if you're not already familiar, and so that's quite nice to include as well. Okay, so I think it's time to go ahead and turn this on. So if we turn the device over, we can see that actually batteries are included, which is a nice feature. There's an IC on the top left, which we will talk a little bit about more later. Power switch that we saw, and the reset button. So let's turn it on. And if we look on the front, we see the LEDs begin to illuminate in some kind of flashing pattern, and eventually they settle down into this counting notion. Okay, so we see EE, EF, FO, F1, and so forth. We can adjust the speed by turning this to the right, and this will make the pattern go faster, or all the way to the left, and the pattern will go very, very slowly indeed. There we go. So let's put that back on the stand and let's look a bit more closely at those instructions. So here it tells us that we have a 6502 microprocessor, which we've already identified. It says they were introduced in the 1970s, and they were important because they were featured in machines such as the Apple II, the Commodore 64, and the Nintendo Entertainment System, or NES. Now, if you're British like I am, you might realise that they also featured in the BBC Micro series of computers. Now, it explains what's going on with the desk ornament and says that the desk ornament contains or displays the lower 8 bits of the 16-bit address bus via the green LEDs. And so these are the lower 8 bits of the address bus. And there will be another sort of 8 over here that represent the full 16, but they're not being rendered or displayed. It tells us that the least significant bit is on the right-hand side, just as it would be in decimal as well, and that's how I was able to read off the values that we saw earlier. It also tells us the data bus on a 6502 is 8 bits wide, and in this case, in this particular device, it's been hardwired to EA in hexadecimal, and if we look up an EA in the instruction set for 6502, we'll find out it means no operation or no op. Now it says that it's going to count through all of the address lines, and that's what's going on here. So the reason this works is that the 6502 looks at the current address, asks what it should do, it finds that it has nothing to do with a no op instruction, and so it goes to the next address and then asks the same thing, finds out what's there, so tries to decode it to tell it what to do, and again finds out it has nothing to do. And that repeats infinitely, and so it ends up just counting through all of the address space, and we can see that happening on the LED display. Now, the way the 6502 actually works when it turns on is kind of interesting, and so we can actually look through that right now together. So on the back, there is that reset button, and so I'm going to press it in just a moment. And what it will do is it will step through 7 cycles where it's configuring the chip itself, setting up its initialization state. It will go ahead and read the values from the memory location EC and ED, and that's what's called the reset vector, which tells it where it should execute code from. And in this case, because the data bus is hardwired to EA, it's going to receive EA for both of those values. That means it will start trying to execute code from EA, and that would be EA represented over here, which we can't see, but it will also show EA on the display, and that'll be the first place it starts looking for code, and that's why it will count from EA onwards. So let's go ahead and reset the device, and then we can see the initialization happening. and it's getting the reset vector in just one moment now, and the second part, and then we can see it's starting to try and execute code from the address EA. Now I'm holding down the reset button here to freeze the processor, and we can actually read that off, and we can see the E there and the A. So E because of 8 plus 4 plus 2, which is 14, or E, and then we have over here, we have 8 plus 2, which is 10, or A. If I let go of the reset button, the processor will reset, but then it will begin through the process again and eventually start counting. So I'm going to do that now. And so the reset will proceed again. And we're getting the EC value, ED value, and we start at EA, EB, EC, ED, EE, EF, F0, F1, and so forth. So this is a wonderful little desk ornament, and I think it's going to look fabulous in my office. But I think it's also a little bit sad that such a competent processor is sitting there doing nothing all day, getting no op after no op after no op. So I thought what would be fun is to extend this circuit ever so slightly so the processor can stretch its legs a little, maybe do some calculations, maybe some I/O. But the first thing we're going to need to do is recreate this circuit on a breadboard, and so that's what we'll be doing next. On the back of the device, there's a small IC that I pointed out earlier, and although it will be impossible to see on the camera, it's labelled as the LMC555CM, and that's just a low voltage CMOS version of the classic 555 timer, and it allows us to run it from the two AA batteries that are pre-installed in the device. Now, in combination with the control on the front, that sets the clock frequency of the CPU, and by extension controls how fast it accesses the address bus and illuminates the LEDs on the front of the device. And so therefore that's the first thing I'm going to need to build on my breadboard, some kind of clock source based on a 555 timer. So let's turn this off, move it out of the way, and bring in my breadboard. So you can see I already have some circuitry pre-installed on this breadboard, and the 555 timer is at the top of the board just here. Now if we look at the datasheet for a 555, just as follows, we can see here is the pinout of a 555 timer, here's the functional block diagram, and we also have a astable operation diagram as well that allows us to generate a square wave that we can use as a clock signal for our 6502. Now I followed this diagram almost exactly. The only modifications I've made are firstly in this load resistor here, I've gone ahead and added an LED as well, and this allows us to see the frequency that we're actually pulsing at. I've not left the control pin open, instead I followed note A and added a decoupling capacitor just here. And finally, I've replaced resistor B here with this variable resistor, and that allows us to set the speed just as we can do on the original desk ornament with that blue control. Now, as you can see, the classic 555 timer works at 5 volts, and I am using a classic 555, so I'm going to need to set my power supply to at least 5 volts, and I can go ahead and do that here. So if we just turn this up slightly, bring it just over 5 volts. So now I'm going to go ahead and connect the red wire and the black wire to the black wire, and we see our LED is now flashing. Now, as I mentioned, we can control the speed with this variable resistor here, and I have a screwdriver for that purpose. I'll just pop that in, and if I turn to the right, LED will get faster and faster, and if I turn it to the left, it will get slower and slower, and that's the same as on the original. Now I'm going to leave it somewhere in the middle so that we have a reasonably paced clock signal for our 6502. On the bottom of the board, I have some components already set up, and this is ready to accept our 6502 processor. And in fact, I am going to use the 6502 that is provided in the desk ornament. So I think it's about time we liberated this 6502 from its no-op prison. And to do so, I'm just going to use these tweezers and gently prise between the socket and the processor to be careful not to bend those pins. I do think it's nice that it was provided in a socket. That means that you can take it out if you choose to do so. Now we don't want to install it while the power's on, so let's disconnect the power and install the CPU. Let's look at the circuitry that was pre-installed on the lower breadboard and that now surrounds the 6502 processor. Along the bottom here, we have 4 red jumper wires that tie 4 of the pins straight to the 5-volt rail. Now these pins are important because the first one is the ready pin, and we need to keep that high to indicate that the CPU should operate. The next 2 are the IRQ or interrupt request and NMI or non-maskable interrupt pins, and both of these should be kept high unless we want to interrupt the processor by bringing them low. Now we're never going to interrupt the processor during this operation, so we're going to go ahead and tie them both to the 5-volt rail. The next red jumper is connecting to the VDD or power pin, and of course that does need to be connected to 5 volts. Moving further along, we have the address bus, and the lower 8 bits of the address bus have been connected via these blue wires to some LEDs, and these are in a LED bar format just for convenience. And likewise, they're connected to a resistor pack, which is 8 resistors, all connected to a single ground point that allows us to connect through to ground, and that controls the current through the LEDs while allowing us to monitor the lower 8 bits on the address bus. And that's the same we find in the original desk ornament, where there are 8 LEDs, and these are connected to the lower 8 bits of the address bus. As we're not monitoring the higher 8 bits of the address bus, the next pin of interest is the VSS or ground pin, and you can see that's connected just here to the ground rail. Next along we have 8 resistors just here, and these are connected to the data bus. Now they're currently configured to provide the instruction EA, just as in the desk ornament version, but I'll discuss that a little more in a moment. The next 2 red jumpers are again important and tie us to the higher or 5-volt rail. And the first one is the bus enable pin on the right hand side, and that ensures that the CPU is allowed to access the address bus and the data bus. Without access, it wouldn't be able to do anything. The final red jumper on the left is the set overflow flag jumper. Now this is used to set the overflow flag in the processor and provides an easy and quick way of indicating a status change to the chip. But the manufacturer of this particular chip recommends against that use, and so we're just tying that to 5 volts to disable that functionality. The final pin on the chip is being tied to 5 volts using this resistor here, and that's the reset pin. Now the reason we're using a resistor rather than just a jumper is it means we can also connect to this button here that connects through to ground, and that allows us to press the button, and that will short this pin to ground and reset the processor. By default, you must hold that pin high for the processor to operate. Now there's one final connection we need to make, and that's from the clock to the chip. And so we're going to move this orange wire here, just as follows, and connect it to the phase input or clock input on the CPU. Now, before we turn this on, let's look more closely at those resistors and see how they're connected to the data bus. Now, I already mentioned they are representing the EA instruction that we saw on the original desk ornament, but let's look a little bit more closely and see how that works. Now, the least significant bit is on the left-hand side, so we're going to read from right to left. But if we look along here, the first 4 resistors, we see high, 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 and low. And so that represents 1, 1, 1, 0. And if we add those up, that's 8 plus 4 plus 2, or 14, which is known as an E in hexadecimal. So that's the E. If we look at the next 4 resistors, we see a high resistor, a low resistor, a high resistor, and a low resistor. And this represents 10, 10, or 8 plus 0 plus 2 plus 0, or 10. And in hexadecimal, a 10 is an A, and so that's where we get the EA from. So I think we're now ready to power this up and see what actually happens. So again, I'm just going to bring in my power supply leads here. We have red and black. And we can see the clock is flashing. We can see the initialization happening. And now we see the processor is counting in binary, just as it did on the original desk ornament. So I think we've successfully recreated the desk ornament. I'm just going to show that we can also still adjust the speed by using the screwdriver in the variable resistor. So if I speed this up, we can see very fast, and I can slow this down as well. I did say we'd let the processor stretch its legs a little and do some calculations. At present, these resistors hard-code EA onto the data bus, and therefore the CPU always carries out that no-op instruction. But there's no reason we had to choose the no-op instruction at all. In fact, there are a variety of different instructions we could have considered. I've printed out this instant reference card for the 6502 processor, and there are a variety of instructions available that don't manipulate the address bus, and therefore would have been suitable for the binary counter application. For example, we have the ADC instruction here, which takes a single immediate value. Now, as the opcode is 69 and we're hard coding, That means we'd only ever be able to add 69 to the accumulator, but that may have been nice. Instead, I was really looking for a single byte instruction. And so we can look along the list available here and we see things like CLC that clears the carry bit, not particularly interesting. Or we have some on the right-hand side, including logical shift right, and we have the rotate through carry, which might have been interesting as well. The problem with these instructions is we don't know what's in the register they're manipulating. And so if they're all ones, for example, maybe we're just creating a loop of ones, or all zeros, a loop of zeros, and that might not be as interesting as we might have hoped. There are a few more instructions, some to do with returning from interrupts or returning from subroutines, and a few down the bottom for manipulating data, moving data between registers. But again, unless we know what that data is, we don't really know what we're shuffling about. On the left-hand side here, though, there are a couple of instructions which do manipulate data in predictable ways that might be interesting. We have the decrement instructions. We can decrement the X register and the Y register by 1, and these are single byte instructions. Or we can increment the register X and Y as well with a single byte instruction. Now, as we're already counting up on the addresses, I thought it might be interesting to count down, so we can use a decrement instruction. And so there's one here, the DEY instruction with the opcode 88. I thought that might be easy to implement with only 2 high bits. And so let's go ahead and install that on the breadboard now. To change the opcode, all we need to do is manipulate these resistors, so they now represent the pattern 88. So our resistors on the data bus are now representing high, low, 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 or 8 plus 0 plus 0 plus 0 for a total of 8. And then the next 4 resistors are high, low, low, low. So again, 8 plus 0 plus 0 plus 0 for a total of 8. So overall, we're representing a hex value of 8, 8. So we can go ahead and we can connect up the power now and see how this operates. So just as before, we go through the initialization routine and then we begin counting. But you might notice that we're now counting from a different position because now our value is always 8, 8. And so therefore our starting location is 88, 88. And because we're only monitoring the lower position on the address bus, we see it starting counting from 8, 8. If I reset the processor, you'll see it go through the initialization, load the reset vector, and therefore start counting from 88, 89, 8A, 8B, 8C, 8D, 8E, 8F, and so forth. As the processor continues to count up on the address bus, it should also be decrementing the Y register. However, we have no visibility to what's going on inside the chip. So our next task is to try and get the processor to tell us what's going on in Y. Let's take a closer look at the instant reference card. At the bottom here, you'll see a few instructions for storing Y, and what this really means is to put the value of Y on the data bus. What's really interesting, however, is that one of those instructions has the opcode 8C, and what we're currently doing, the decrement Y, has an opcode of 88. The difference between these two instructions is just 1 bit. So if we want to convert every alternate instruction from 88 to 8C, all we need to do is to assert the third bit on every alternate address read. Fortunately, we already have something that asserts a single bit on every alternate address read. That's the lower bit on the address bus. So let's disconnect the power and see how we can go ahead to do that. I've just grabbed this diode from a random selection I had available. What I'm going to do is I'm going to use it to tie the first bit on the address bus to the third bit on the data bus. What this means is that for odd addresses, we're going to read the value 8C on the data bus, but for even addresses, we'll continue to see the value 88. Let's take a look at how the processor is going to interpret these series of instructions. After initialization, it's going to access the reset vector at FFFC, which is an even address, and so it will receive the data 88. This is the least significant byte of the reset vector. Next, it will retrieve the most significant byte of the reset vector from address FFFD. As this is odd, it will receive an 8C. This means the processor will try and begin execution from 8C, 88. But again, we're only looking at the lower half of the address bus, and so we'll only see 88 on the display. At this point, it will load from address 8C88, which is an even address, which will mean it will load the DEY instruction to decrement the Y register. The next instruction, 8C89, is an odd instruction, and so we will see an 8C. But the store Y instruction here is actually a 3-byte instruction, so it's going to go ahead and read 2 more bytes to find out the address at where it should store the data. It's going to retrieve 88 and 8C respectively, which will be interpreted as 8C88. At this point, the processor will assert 8C88 on the address bus, and then go ahead and write the value of the Y register onto the data bus. Once it's completed the write, the processor will fetch the next instruction, in this case from 8C8C, where it will continue our program, fetching another DEY instruction. So let's apply some power and see how it works. Once the processor has initialized and loaded the reset vector, it begins running our new dynamic program. After before address reads, you'll notice the processor asserts 88 on the address bus. This is the lower half of 8C88, the address to which the processor is trying to write the value of the Y register by outputting it on the data bus. Unfortunately, we don't have any visibility into what's actually going on the data bus. So what we need to do is add a few more LEDs to monitor that output. So let's turn off the power and connect up our new display. This breadboard contains another LED bar display and a resistor pack to allow us to limit the current. But in addition, it contains a 74HC573, a transparent 8-bit data latch. So in addition to allowing us to monitor what's going on the data bus on the LEDs, this chip will allow us to store the value the processor is trying to write to the data bus. Let's pop it down and wire it in and see how it works. This is the datasheet for the latch. It allows us to pass data from 1D to 1Q and store the value inside the chip. In addition to power on pin 20 and ground on pin 10, we also have an output control on pin 1. This allows us to turn off the output and disconnect them from the bus. In our case, we're going to tie this to ground to ensure that it's always active. It also has a control line here. When the control line is high, data from the input is stored into the chip and passed through to the output. If we want to freeze the data that's in the chip, we can set the control pin low, and we'll see more on that later. I've already connected power and ground, as well as tying output enable low to ensure the outputs are always enabled. For now, I've also connected the control or enable pin high using a resistor. This means that data will pass through the chip right out to the LEDs. So let's go ahead and connect up the data bus. So let's reconnect the power and monitor what's going on. Once the program is running, we can see the value of the data bus on the top row of LEDs. You'll see it mainly switches between A8 and 8C, our two instructions. But periodically, you'll see it flash a new value. This is the value of the Y register that the processor is writing to the data bus using the STY instruction. While it's nice to be able to see that the program is running correctly, what would be better is if we could freeze the LED display with just the value that was written by the processor. Looking at our reference card, we can see that one of the pins on the processor tells us whether or not it is trying to read or write to the data bus. Unfortunately, our latch requires a high value on this pin to allow the data to be stored, and the processor provides a low value when it is writing data. Fortunately, we can fix this quite easily with an inverter. I could use a dedicated inverter chip, but instead I'm going to use this BC547 transistor. All I'm going to do is pop it in the breadboard right here. The BC547 is an NPN transistor. By connecting the collector to 5 volts via a resistor and tying the emitter directly to ground, this means any signal I apply to the base is inverted at the collector. By connecting the read-write pin on the processor to the base of the transistor, any attempt to write will now activate the latch. Now we can see the value that the processor is placing on the data bus is being stored in the latch. However, between updates we see a brief flash of 88. This is invalid data on the data bus and is a consequence of our resistors, but let's take a peek at the datasheet to see if we can understand exactly why. This is a timing diagram from the 65CE02, a CMOS version of the 6502. It's actually from a slightly different processor, but I find this diagram a little bit easier to understand. It's a timing diagram, so time moves from the left to the right. We can see various clock signals, including our input clock and 2 subsequent clocks that the processor produces, as well as information about the read-write line, the address line, and the data write process. In our case, we want to monitor when the data write line goes low, and we need to make sure that we have valid data. But if you look at this diagram here, you can see the read-write line will go low far before the data is valid. In fact, there's no minimum time for the TRWS, so this could happen as soon as the clock cycle changes. And TMDS, the time it takes for the data to become valid, could be as long as 30% of the entire clock cycle. This means that there is no valid data in the first 50% and potentially no valid data for another 30% of the clock cycle, a total of 80% of the clock cycle. As the valid data only occurs in the second half of the clock cycle, what we could do is we could use some signal to indicate that we're in the second half of the clock cycle and use that, as well as the write line going low, to indicate that we should read to the latch. In our case, we can use O1. If we make sure that both O1 and read-write are low, then we're only recording data in the second half of the clock cycle. If either O1 or the read-write line are high, we should disable the latch. This will remove much of the invalid data. We can make a simple OR gate to make sure neither O1 or read-write are high using a pair of diodes. The O1 output is on pin 3 of the processor. Now, as before, the latch won't be able to store any data whenever the read-write pin is high, indicating the processor is reading from the data bus. But also, it won't be able to store any data whenever the O1 pin, which is more properly referred to as the phase 1 clock output pin, is high, as this indicates we are in the first half of the clock cycle when we know the data is likely to be invalid. So let's power up the circuit and see what happens now. Now this is working surprisingly well. The latch appears to only be storing valid data from when the processor is writing a value to the data bus. We can clearly see the decrementing value in the Y register being displayed on the top row of LEDs. While the address bus is still sequentially counting upwards, we still see a periodic flash of 88. This is the lower half of the address to which the processor is trying to write the data. However, our circuit doesn't care what address is being written to, and the latch simply stores the latest value placed on the data bus. We could devise a more complicated circuit to differentiate between the addresses on the address bus, but for now I think this is complicated enough. If you'd like to learn more about building a 6502 based computer on a breadboard, I'd encourage you to watch the series of videos by Ben Eater. But I hope you found this exploration, recreation, and extension of the Computer Museum of America's 6502 Binary Counter Desktop Ornament interesting, and I hope to speak to you again soon in the next video.